We're about to finish up chapter 3 and moving to chapter 4. Anything at all? Remember the big thing with boundary conditions, 99% of the problems you're going to run into is just the tangent electric field on either side of the planar boundary is going to be the same, and the normal component of the D field will be the same. The exception is if you have a conductor, a perfect conductor, then D normal is going to be the actual surface charge density, rho s. And if you do have a situation where you have a bound charge density, then you have to take A21 dotted into D1 minus D2 and put it equal to rho s. Now, we'll give you that formula, but you have to know how to apply it and use it. So I gave you a bunch of problems related to that, if you look at it. And I can give you a whole bunch more if you want. But the fundamental thing is just get familiar with how to deal with that. You all with me, class? All right. Now, there's something else I'm going to do right now. It's not part of the text, but it's very, not this part, it's later. But it's very useful. I want to show you this. This is called the method of images. So, make sure you see this. Suppose we have a perfect conducting ground plane here. All right? In other words, this would be steel, copper, something like that. You all with me, class? Now, if we have a charge above it, call it a charge Q, and it's at a height h. And we wanted to solve for the electric field anywhere in the region above here. There would be two conditions, really, there's one major condition. The tangent electric field on this boundary would have to be 0 because it is a perfect conductor. Does everybody understand the reason why? If the electric field was non-zero, perfect conductor means sigma goes to infinity. Do y'all follow me? If sigma goes to infinity, any finite value times sigma would give an infinite current density, which is not allowed. Y'all follow me? So the tangent electric field will be 0 if you have a perfect conducting surface. Y'all follow me on this? It's very important. So generally speaking, if we're going to solve for the voltage, say, anywhere up here, the way you would technically have to do it is use something where it'd be something where you're going to do a boundary value problem. I'm basically folding in some theory into this problem, and then I'm going to show you the easy way to solve it. So when you think about electrostatics, it means there's no time-varying electric field you have to worry about. And you start with a basic equation, divergence of D would be equal to rho V generally, right? What do we call that? There's a name for it. There's a famous guy, Gauss, right? That's the differential form of Gauss's law. Then, if you know that D is equal to epsilon E, right? You can see the divergence of D, or epsilon E, is equal to rho V, and divergence of E. Now, this assumes that epsilon is not a function that varies spatially. If it is, this wouldn't work. Y'all follow me on this? If it was, then you'd have to take the divergence of this, it breaks it up into a gradient of epsilon, and then it's going to be times, or dotted with E plus, epsilon times the divergency. But I don't want to go there now. Just saying it's more complicated if epsilon is a function of the actual position. Do y'all follow me, class? So it becomes divergence of E is simply rho V over epsilon. Now, this is very commonly seen everywhere. And I think in physics, I've even seen somebody showing me stuff where they use that form of Gauss's law, D is a form of Gauss's law, to solve problems instead of divergence of D. But that doesn't matter. Now, E itself is equal to minus the gradient of voltage. Do y'all remember that? And I've made a big spiel about saying how if V is a scalar, so if we can find V from any charge configuration as a function of position, we can simply take the gradient of that and get the E field. You all follow me? It's very important. And if you do numerical method stuff, you're going to see this stuff saves your life many times, just knowing it. Now, if I take this and stick it in here, I get divergence of minus the gradient of V is equal to rho V over epsilon. Does everybody follow me on this? And epsilon is epsilon relative to epsilon naught, technically. You good with this, everyone? Now you can take the minus sign to the other side if you want. And now we define the Laplacian. This is simply the del squared of V is equal to minus rho V over epsilon naught. This actually is called Poisson's equation. Do you all remember that? Did you see this in physics? How many did? Jonathan, did you see it in physics or not? No? Okay. Nobody saw it in physics. This used to be a mainstay thing. The guy would just kind of build up to it and then ta-da. It doesn't mean anything, the form it's at. But the thing about this is, that is called the del squared operator. If you look, it's a scalar thing. If you look in the back of your book, hope you have books, right back here, that's the last thing. It's called the Laplacian. They give it to you in cylindrical, spherical, Cartesian coordinates. You all see it in the back? Now that right there is a second order differential equation. What's given there is only for the voltage. These are all scalar Laplacians. Technically, the Laplacian operator has a vector component that we'll see later. And a vector del squared is much more complicated in spherical and Cartesian coordinates. But you at least need to be aware of it. Now, if you look in the back of the book here, you're going to see we've talked about divergence right here. We've talked about gradient right here. We haven't really talked about curl yet. That comes later. It comes in the next chapter. And now we've talked about Laplacian. So 3 of the 4 major operators in the back of the book we've covered right there. I mean, in the back cover of the book. Now we're going to apply some of these things. So that right there, that del squared equation, is something that's in section 313 for boundary value problems, but it doesn't mean a whole lot by itself. I'm just going to show you something, try to introduce this in a way that makes sense, not just throw a bunch of abstract concepts in. So again, this is a differential. Did you have a question? Go ahead.
So this Laplacian only works if epsilon naught doesn't vary.
If epsilon relative is not a function of the position, spatial position. If it is, then you've got to go back to this thing right here, and you have to do the operation. I'm just going to tell you, I don't want to spend more than a second on this, but if that was spatially dependent, then you would get the gradient of epsilon dotted into the E field, plus then it would be epsilon times del squared, divergence of E. I'm just going to say that's going to become here, the gradient of that will cause this thing to not be as simple as it looks. I'm just going to level it. You don't need to worry about that. That's advanced. That's for, you ever get into plasma physics and stuff like that? You know what plasmas are? Ionized gases. They have a huge gradient, the value of the density of charge, the charge density around certain areas, that causes a change in epsilon, and it's a pain in the butt. Anyway, that's what happens. That's where that one's coming. In fact, my master's work was with plasma stuff, so I became all too familiar with all the pains of dealing with it. Back to this thing right here. Now I want to just show you this applied. Then I'm going to come back to this problem. And again, this can be used to solve this. I showed you a charge there. Usually what they do is instead, if this is just a differential or a point charge, what they normally do is say that it's got some value Q, and they'll put a delta of R there. You know what a delta function is? In your own words, what is it? Think of back in the day when you did circuits. What did a delta function tell you? Or system, linear systems. Well, if you integrated a delta function in the time domain, from minus infinity to infinity, dt, you got 1, right? It said the area under that curve was 1, but what about the height? At the point where the delta function goes from nothing to everything, it goes to infinity. So the product of the width times the height is 1 for a delta function, if you remember it. Do you all remember that? All right. You don't remember a delta function? Dirac delta, is that one of the terms? You call it delta function, right? The delta function is derivative of u of t, if you know what u of t is with respect to time. That's all it is, if it's in the time domain. But anyway, that's how you do it. Then you take that right there, and you put it over here, and you solve the thing. It's a mess. Go to grad school, it's a doctoral program. You'd have to do this just to experience the pain once for yourself. So Never want to do that again if you don't have to, and that's what I'm about to lead up to. So, just to try to bring this to life, let's see how this would work for something that you know the answer to, okay? And let me erase this and just work on this part of the board. Trying to get through this in a way where I don't run just too quickly, but you'll see it applied. Now, this is again in your book in 3.13. I don't know the page number. If somebody can give it to me. You got it right there?
190.
190 in your book. So we're going to do a classic problem. Suppose I have something, doesn't matter. I've got an inner radius of A, and I've got an outer radius of B, and let's go in spherical coordinates. All right? Let's call between these two things, just have epsilon naught as the permittivity. Now, if I asked you to solve for the voltage anywhere between these two, and I said the outer part was grounded, and the inner part had a voltage V naught on it. Remember before we used to always assume a charge. Remember how we find capacitance for those problems? You assume a charge, then you get the D field, then you get the E field, then you integrate the thing and you find the voltage difference between the plates, and lo and behold, from that you find the capacitance as Q over V. And that works. But this is going at it in a different way. I'm saying the potential here is V naught, and this potential would be 0 volts. So I come over here and I have the del squared equation. Del squared of V equals, now I'm worried about the potential between here and here. I know that there's a positive charge density on the surface here, rho s, but I don't need to worry about that. Between here and here, there is no bound charge. Do you all follow me, class? In other words, this region could be a vacuum for all you care about. So I come over here, that means this is 0. Now, if you look at the back of your book, the back cover of your book, you're going to see a del squared spherical coordinated operator. You all with me? You have your books, guys? If you don't trust me on this one, you can take a look, tell me if I'm right or wrong. This del squared in spherical is going to have 1 over r squared ddr of r squared times dv dr equal, and the reason I'm only putting one term there is I'm assuming an argument of symmetry where v is not going to be a function of theta or phi. Y'all follow me? But if you look in the book, there are 2 other derivative components. Can you all see that if you're looking? All right? That's the way you'd have to do it in the general sense. If you couldn't assume symmetry, you'd have to do that. And I might add, solving a problem like that, where you can't assume symmetry, most of the time doesn't have a closed form solution. You have to use a computer to solve it. I'm just saying this. You have to do numerical simulations. You familiar with this? You're smiling and nodding your head. I'm going to level. Has anybody solved things numerically that have to do with differential equations? Anybody? What did you solve? I'm just curious.
Mass on a spring.
All right. See, that's just a linear first order kind of thing. It's a second order differential equation, but it's 1 degree of motion. This is 3 degrees spatially, right? We have 3 possible degrees, and it's not a function of time, but these things are a nightmare a lot of times to solve in a closed form. However, thank God for computers, because with finite element, finite difference, and even there's methods that are hybrid. You can solve these things in no time, very easily. So if you look at this, let me go through this. So y'all follow me, that's it, right? Let's multiply everything by r squared. Well, r squared times 0 is still 0. Now integrate both sides, and you're going to get r squared dv dr, and that would be some constant c1. Y'all follow me on this, guys? You integrate both sides, right? Anytime you do an integration without hard limits, we're not putting hard limits here, we'll get those from the boundary values, you have to put a constant c. You do. Now, after that, I divide by r squared, and then I integrate again, and that means I have v of r is equal to some, it'd be minus C1 over R plus C2. Can you all follow me on that? That's a second constant. Now the truth is this. A constant undefined allows you to change, get rid of the negative sign. Do y'all follow me in this class? It doesn't matter if it's plus or minus, we haven't evaluated. So I'm going to do this just to make my life easy. And then I'll make this minus, just because I don't like to complicate things. I know the answer to this, so I'm making it user-friendly at this point. You don't have to do this. Y'all with me, class? All right, so I come over here. Here's my general voltage equation. And you think about that. Now we do boundary values. What are the two boundaries that we know? At R equals A, we have V naught. Everybody see that? And at R equals B, we have 0, right? So now we solve for the two constants. And I'll do that here. So, from that thing, I have V of A equals to V0 equals to C1 over R plus C2. And I have 0 is equal to C1 over B plus C2, right? Maybe I didn't put that on here. This should be the distance B. Y'all follow me? We have two equations, two unknowns. We can solve for the constant, solve for V. So probably an easy way is to see C2 is just minus C1B. You agree with that? All right, there's C2. Take that to the minus C1B. So I have V naught equal to C1, and over here, since it's an A, I should have made this A. C1 over A plus C2, and C2 would be minus C1 over B. And you can see we've got V naught is equal to C1 times the quantity 1 over A minus 1 over B, or C1 itself is just equal to V naught over 1 over A plus, or sorry, minus 1 over B. And now we can write the general form of the equation, because I've got C1 as such, and that means C2 itself would be equal to minus C1 or minus V naught over 1 over A minus 1 over B. And it's going to be divided by B. So it's divided by B down here. And you can carry it through if you want. So I have C2 is equal to minus V naught over B over A minus 1. Doesn't matter what form it is, but y'all follow me on this? I'm just taking it down to the last step. Finally, I get a general equation for the voltage. And I can do it right here. I'll put in, this is equal to C1 over R plus C2. And now I get C1 is V naught, if this is simplified, over 1 over A minus 1 over B divided by R plus C2, which is actually a minus V naught, and it's going to be divided by B over A minus 1. And that's the equation for V of R. Y'all follow me on this? I went through it. I'm trying to just show you the steps. Now again, you've got it. Really, you can condense, if you know what the voltage is, and you know a B and A, that becomes a single constant, right? This right here, the V naught, 1 over A minus 1 over B, that's another constant, but that's the form. Y'all with me? Now, the next thing, if you wanted to, that's the voltage. If we wanted the capacitance, where would we go now? This is a tricky one. Think for a second. I'll give you a second. I've got the voltage, right? You agree? Can I get the E field? Matter of fact, I erased it, but I had the E field up here, didn't I, class? Or I had dVdr. So if you go ahead and you take minus the gradient of that, which will be just minus dV/dr. Y'all hear me? You're going to get the E field. How many understand that? Now, if I have the E field, can I get the D field? What do I need to do? Multiply by epsilon naught, right? Now, if I have the D field, this is very important. I didn't say this specifically, but this is a perfect conducting surface. Do y'all follow me on that? If you have the D field, what did I tell you about the D field's relationship to charge density on a perfect conducting surface? D normal is equal to the charge density, right? How many remember that? Follow me on this? Now, if you know the charge, therefore, if you know the D field, it will be normal here. You take that and you would simply find the D field at this point, multiply by 4 pi A squared, and you would have the charge. Do you all follow me? Then you would take that value of charge, divided by what? The voltage, and you would have the capacitance. Do you all see this, class? So this is a reverse kind of problem, but you can do it that way too. I'm going to give you this one. Make sure you know how to do this problem in its entirety. And it's good. However, one of the things you probably appreciated with the fact that there's a lot of steps involved in that. Now, if you were to use the same idea as I had, the way I did the differential equation and solve it for this problem, where you've got a perfect conducting plane, now you get into something where you're going to get all these infinite series solutions at this point. I'm not going to do it, but I'm just telling you, which is a pain in the butt. I hope you agree with that. I don't like to do enormous amounts of mathematics if I don't have to, and there's an easier way. Here's the easier way. Now, hear me. So what we do, and I'm just throwing that up there as an example of solving the del squared equation, because it's important to know that, but here's how we do it. We do something called the method of images. I want you to write this down. So, now, to tell you about the method of images, and it's a very powerful and useful technique. Here's what goes on. What we do is say that, let me just be clear about this. I'm going to assume I have a charge right here at a height h of just q. And what I'm trying to do is figure out the voltage everywhere in this plane. Do y'all follow me? And I can't prove this mathematically in the time I have. But what I can do is this. Remember this. I can say if this is a plus q, what will actually happen is that plus q will pull up charge, negative charge on the ground plane. And it'll be distributed in a way that's kind of interesting. It has it's close to a Gaussian distribution, but I'm not going to get there. But the net effect can be mathematically, and this is exact, can be mathematically equivalent to putting a charge of simply minus q at a height of h below the ground plane. Now, please listen. Y'all follow me? This is called an image charge. So that was a positive charge. Here we put a negative charge. And then we ignore this boundary. And we're going to find the voltage from those two charges up in this plane. Do y'all follow me in this class? So if I have this, and I have a distance r1 here, and we assume the voltage at infinity is 0, well, if the voltage from this charge at r1 will just be equal to q plus over 4 pi epsilon naught r1. It's a scalar value. Do you all follow me? Think about just a point charge in free space and assume the voltage at infinity is 0. The voltage anywhere from that charge is just divided by 4, take q, divide by 4 pi epsilon naught r, and you got it. You with me on this? And the only thing you need to know is the distance r1 from that charge. Now down here, you've got to get the voltage from this, which would be minus Q over 4 pi epsilon naught, for epsilon, it doesn't have to be epsilon naught, epsilon R2. Now both R2 and R1 only depend on the distance that you are from those two charges. So it depends on your coordinate system. If you're in Cartesian coordinates, you can get these by just doing geometries, right? You can get these very easily. Now once you have that voltage, it is a function of position, right? How would you get the E field? Remember I told you? I mean, I can go through all the steps, but that voltage is doable. Do you agree with that? Now how do you get the E field? Always. Minus the gradient of the voltage is the E field. So if you wanted the E field anywhere, and it would only be in the upper plane, would not be here, below that, to get the E field, the only thing you're going to do is take minus the gradient of the voltage. You would have the E field. Now, if you wanted to get the D field, what would you do? We know what? Epsilon times E is D, isn't it? So you'd multiply with the E field by epsilon, wouldn't you? So if this is the E field, if I wanted the D field, you'd say simply minus epsilon times the gradient of V. Now you have the D field. This is the interesting thing when you do this. You will find that when you're at this surface right here, there is no D field that is in the horizontal direction. It's all normal. You all follow me? So because of that, you can find the charge density right there just by finding the D field at that horizon line, and you will get it. You all with me, class? And it's a very, very useful technique. It's later in the book, but I wanted to show you this here. Has anybody ever seen this? Because one of the things I tend to do, on final exams especially, is I will give, assuming I cover this technique, a ground plane, and I'll give a charge, and I'll say assume the voltage at infinity 0, and I'll ask for the D field at some point on the ground plane, or the charge density. And you would, now I'm telegraphing this punch coming, so just be ready for that thing, and I will give you some problems like this. You all with me in this class? This is very beneficial. He doesn't cover this technique, but it is so easy to do, and it's trivial compared to solving the del squared of the voltage equation over an entire upper plane. You have to do that in graduate school. Advanced graduate electromagnetic stuff. But this is trivial to do it that way. All right. Next thing we cover is going to be the energy density. This is the last thing I'm going to cover. I'll give you some problems related to that boundary value problem business, because really in engineering you have to understand this. Almost everything that you're dealing with is using integral differential equations to do either solutions, if you're doing analysis to problems, or you're going to use them to design something that will actually work the way you want. Now that is if you're in an environment where there's a continuous possible values to the fields and things like this. If you have any kind of discrete things, then instead of differential equations, you get difference equations. And then you have some difference kind of equations that are integrated to do it. But in either case, you have to learn how to use these things efficiently and accurately to solve things or design things. Okay, next thing we talk about is energy density. So, what are the units for energy typically? Keep it MKS or SI. Joules, right? Joules are a thing that, when I was young, joules. I'm not used to thinking that way. But BTUs are even worse. So I went with joules, and that is the standard thing. When you talk about that, if you have a density of joules or energy, then joules per meter cubed would be energy density. Do you all follow me? Density implies an amount over a certain volume or surface area. So energy density, when we talk about electrical or electrostatic energy density, this is really electrostatic. What that is, a symbol, Whitmore's book likes to do this, is really going to be 1/2, and it's D dot E. Now, D field and E field are related by epsilon. D is epsilon E. So the way it's usually rendered is simply 1/2, and then it's going to be magnitude of E squared, and it's going to be times epsilon. I'll put the epsilon right here. In fact, let me do it this way. 1/2 epsilon E squared. The units would be joules per meter cubed. Can you find that in your book? It's near the end of that chapter 3. And just tell me where it is. What page?
I think 202.
202, anybody confirm that? You see it or not?
It's 198.
198, okay, 198. This is on page 198. This is important. Okay, so that's energy density. Now, I'm going to add this right now. Energy density is one thing. That's how much energy is available to use, but there's power density. This is energy density. So power density. Power density, I'm going to use this symbol, PD, is going to be sigma times, it's really going to be J dot with E, but J is sigma E, so the way it's usually rendered is sigma times the magnitude of E squared, and that's watts per meter squared, or meter cubed, pardon. I'm just doing this for a reason, to make sure I contrast things that you can confuse. Here, this electrostatic energy density is something, that energy you can get back. That is something that's there, and I'm talking about electrostatics, like in a capacitor. When you charge up a capacitor, you're going to have an electric field that surrounds it and is between the plates. It would have an energy density at any point in space. It would be 1/2 epsilon E squared. If you want the total energy, you would integrate that over all space. And you know, if you have a capacitor, the amount of energy is 1/2 CV squared, don't you, class? Well, that energy is available to be reclaimed. You can put a resistor across that capacitor, and it'll short it out, it'll cause current. All that energy will be dissipated by heat in the resistor. This is power density. This tells you how much power is actually being dissipated. And whenever you talk about power being dissipated, it's heat. All right, that's 90% of it. There are things where you have lights that create photons that launch them. You also have antennas that take electrical current, accelerated electrical current, and they create photons that are launched. That has to do with the radiation resistance. But most of the time in the real world, when you talk about power density, you're talking about something that's relating to taking electrical current and creating thermal energy or heat. Y'all follow me in this class? It's just a reality. But these two are the things that are in the book, and he talks about. I will say one thing, since I'm going to finish this up right here. Because this is the section I'm talking about is right on page 198, it's the very last section. He doesn't have a whole lot there. He just kind of throws this stuff out there. But where this is useful, or where this actually comes to play, is when you have an environment and you know not just the electrical properties of it, but you've had chemistry, you know what the specific heat is and things like that. All right, when you're talking about this, if we're dissipating heat in a region and we know the material is dissipating, then the temperature will go up based on something called the specific heat. Do you all remember that? And there's other equations. So the reason this is important is when you're doing a problem that's complicated, where you have materials that have certain different specific heats, and you want to see if the thing is actually going to heat up to a point where it will melt or catch fire or something, then you have to understand, you have to go ahead and write the equations that are important in terms of the power dissipated and the actual electrostatic power the density of the electrostatic energy. Now, I gotta say one other thing about this, and this is important. So you see this term right here? That's electrostatic energy density. When you have antennas, you would like to have, for most cases, especially radar antennas, a very high-powered signal. You'd like to launch a huge amount of power, but there's something that happens. As you get more and more, the electric field that you're going to be launching, this comes later, gets higher and higher, you reach something that's called the breakdown threshold of the atmosphere. All right, you all seen sparks, right? Lightning? What happens is, there's a dielectric breakdown strength in the atmosphere. Does anybody know what it is for the atmosphere, say at ground level, about where we're at? Anybody? It's about 3 million volts per meter. Sounds like a lot. But when you get down to stuff where you talk about volts per millimeter and stuff like that, well, now we're getting about hundreds of thousands, which are not that hard to attain with antennas. But what happens is there's a limit to the amount of power you can radiate from an antenna that deals with both the power density and the electrostatic energy density because of the maximum value of the electric field before you get corona discharge. And here's what happens. When you start approaching that limit, then all of a sudden you'll get this corona. You know what corona is? It's ionization. And you'll see arcing, and nothing will start radiating. It's the upper limit on what you can do. And I'm going to tell you, now, I've never dealt with really super high power stuff like that. But I know it is a problem that I'm very aware of. Just be aware of that. I'll give you some problems that are related to this stuff, but most of the time, the only thing you're doing is figuring out what the electric field is from a given charge system or a current, and then calculating the densities and integrating it over the volume to find the total power or energy that's available. That's it. Now, I said only need two there. So the next thing we're going to do is get in, and I'll give you some problems. Anything you don't do, we'll do in class, but most of these aren't going to be hard. Now we're getting into magnetostatics. That's chapter 4. That's where I wanted to get to. Magnetostatic problems. Well, you've had it in physics. I gotta say that I'll show you how this actually, how they figure out some of this stuff because it's kind of interesting. So, I'm going to start with the general form of the equations. First, when we look at Maxwell's equations, there's going to be a couple of things that are important. Remember when we had, well, let me back it up for a second, right? I start writing differential equations and driving me nuts. If you have your book and you look at chapter 4, you're going to see the first thing he talks about is the definition of a curl. And then, I got a kick out of that, and cross products. He shows you some of these, or a definition of cross products and curls, but the real reason he's doing some of this is to set you up for the next step. So with magnetostatics, and this is chapter 4, if you have a differential amount of current, and before we had a differential amount of charge, so if you have a current I, and it's over a length dl, now dl is going to be a vector, but I'm just trying to show you something. Think of this just like that differential charge we started with. Then, and I'm going to show you where this is in this book. It's on page 214. Then, if you have this, and I come out a distance r away, and I want to know what differential H field is created here. That differential H field will be equal to I dl. Remember, dl is a vector. It has both length and it has it has a direction and a total length, but it's going to be differential, so it's infinitesimally small. Then it's going to be crossed into a unit vector, AR, that goes from the actual source to the point of observation of the H field. And it's over 4 pi, and then it's going to be magnitude of R squared. Now he's going to show you that, And the units of the differential H field will be amps per meter. And in his book, he shows you this in equation 4.4, but he uses AR12, and then he calls this H2, and he likes AR12. Let me just cut to the chase here. When he talks about this, AR12, call this 12, is a unit vector that points from the source to the point of observation of the H field. That's the only thing it means. Y'all with me, class? All right. So how many remember the H field and the B field when you were in physics? That's the big, big deal in physics. Physics guys do this, and usually they talk about the experiments that were necessary to measure these things, and they go through the whole spiel, the history of the world, you might say, related to these measurements. So you have that right here. Now, contrast that to the electric field. When you had a differential charge, dq, right? And you're a distance r away, and you wanted to know what the differential electric field right here was, that was equal to q over 4 pi r squared epsilon naught. Do y'all remember that? And there would be AR here, correct? Do y'all remember? You'll see it's inversely proportional to r squared. There's the 4 pi there, right? You'll notice for the H field, there's not an arbitrary constant epsilon in there. Can you follow me on this, class? They're very similar. The difference, the real difference is this, the cross product operator. But you can see at least there's a lot of similarities. That's the E field for a chunk of charge here at a distance r. That's by Coulomb's law, right? Here it is for the H field, right? Now, the best way to see how this works is apply it to a problem. I'm going to try to do this now. And I'm going to do the classic problem. I don't know what problem he has first, but I'm going to do the one that's just going to be a loop. It's on page 117. This is a classic problem, and I'll try to do a good job. So, remember, when we were talking about when we had the differential charge right there from an electrostatic charge, or differential electric field from a differential charge, and we wanted the total electric field, we found the differential field from a component on the actual charge configuration, whatever it was, at the point of observation, and we integrated that total thing over where the charge exists. Do you all remember at least the steps, right? I call it the building block approach. So, all right, so now call this the z-axis. Please make sure you see this. Usually in physics, they really do a good job at this one, but let's assume we have a loop of radius A, and we're going to put a current I going around it. And it's in the xy plane. Call this x, call this y. So we just have a loop in the xy plane, and what we want is, we want to know what the H field is on the z-axis. That's what we want. So we come down here, and say I have a differential chunk of current here, and call it IDL. And from that, I want to know what the differential H field is. And then I'm going to go ahead and integrate the differential H field, or integrate the effects of the total loop to get the total H field. Find the differential, then integrate over where the charge exists to get the total H field. Do you all follow me on that? Okay, so now we have to say what DH is, and I'll do that over here. So again, the differential H field is equal to IDL over 4 pi r squared, and then it's going to be equal to that crossed into AR12. So now we get the various components that we have to worry about. First thing is, I have to set a height up. So I'm gonna say that this thing is at a height, I'll call it Z, above there. We have the radius A already. With me? So let's do it. So first, when we look at this, I need R vector. So R vector would be measured from here. This is going to be my R vector to that point of observation. And if you look at this, well, we're doing cylindrical coordinates. What's the radius, what radius is associated with the point of observation on the z-axis? Hint on the z-axis? 0, right. So we say R is going to be 0 minus A rho. Do you all follow me on that? Take the position of observation of the field, subtract the position that that's causing the H field, which is at a distance A away. Do you all follow me? Next, what about Z? Position of observation is just Z. What is the position of the current causing it? 0, right? So it's just Z, AZ. Now the phi component loses meaning because we're on the axis. Do you all follow me on this, class? Just go with me on this and I'll explain a little more. On the axis, phi has no definition, right? It's undefined. So this is going to be R, or it's going to be minus A rho plus ZAZ. How do I get the unit vector AR? Well, he calls it AR12. How do we always get a unit vector, class? Take R vector over R magnitude, right? So what's that going to be? That means we have minus A rho plus ZAZ over the magnitude of that, which is simply square root of A squared plus Z squared. Do you all agree with that? Can you all see it back there, by the way? All right. So this is going to be A squared plus Z squared to the 1/2 power. So now I have that, now I have R. Now I need this component, dl. Please watch this. So I need IDL. Well, I is going to be assumed constant all the way around that loop. If it wasn't, we couldn't use any arguments of symmetry. Do you all follow me, class? So here, I'm going to have I. Now, DL, how many remember the wiper arm thing I always talk about? Think about your windshield wiper. If you're at any distance rho away and you have d phi as a distance, the tip moves rho d phi, correct? So here, it's going to be I times A, because that's the radius, and it's going to be d phi, and it would be in the A phi direction. Y'all with me? Okay. Now coming over to here, I rewrite this. And I say it's IDL, and it's going to be I, and then it's going to be A, d phi, right here, in the A phi direction, crossed into this right here, which is minus A rho plus ZAZ, and it's over that to the square root of it, but I'll show you why I'm doing it this way. 4 pi. Now remember, I didn't put this is R, magnitude of R12 right here is just going to be equal to the square root of A squared plus Z squared. Can you all follow me on that, class? I'm just trying to show you all the steps. All right. So I have R squared times AR. I need the magnitude of this down here. When all is said and done, then you get this. You get A squared plus Z squared to the 3/2 power. Simply because you had an R squared to start with, which is just A squared plus Z squared. Then you have to divide it again by the square root of A squared plus Z squared to get the unit vector. Y'all with me? I'm going to finish this. Okay, now, here's the thing. You take a look at that, and this is simply dH, right? To get the total H field, I have to integrate. Before I integrate, I've got to do the go ahead with the product thing right here. So what happens? I find that dH is equal to, first take out the constants. I have IA, right? I have 4 pi. Notice this, neither A nor Z changes anywhere around that loop. Do y'all see that, class? They're the same, that's a constant. That means I can go ahead and take this whole thing out front. All that, I can put A squared plus Z squared to the 3/2 power. And now I'm going to go ahead and do the crossing here. And when I go ahead and do that, I have A phi crossed A rho. What is that? Phi crossed rho is a Z, isn't it? How many have had cross products? Do you remember X cross Y is Z and stuff like this? Well, I'll put this up here. I think I'm out of time, and I got another class that can come in here. But if you have rho crossed into phi, crossed into Z, comes back to rho, these are all positive. If you go the other way, they're all negative. And I don't know if you remember this or not, I'll go through it more next time. So when you do this, this cross this, we got, that's actually a minus, so it's going to be positive AZ. So it's AAZ. And you can see it there, rho phi, you go phi rho, goes minus AZ, and then I'm going to have A phi crossed into AZ, which is A rho. I'm going to have to do this next time to finish it up. But you're going to find out that at the end of the day, we're going to be able to get the H field on the axis very easily. I'm sorry I didn't have enough time to finish this. I'm going to give you some reading to do, try the problems, and we'll see you on Wednesday.